Thank you so much for being here today. I'm Mallory Szymanski, and I'm Assistant Professor of History, and I'm standing in today for my esteemed colleague, Dr. Amos Westacott, who is currently in a car on the road and not in front of a computer. So I'm going to do my best, Amos, to make you proud. And I am delighted today to be here. I'm going to start with the announcement of next week's Berggren Forum, and I'll introduce our guest today. We'll have about a 35-minute presentation, and typical of Berggren Forum, there'll be room for questions and answers. So as you're listening, feel free to enter questions into the chat or hold them to say verbally at the end. Next week's Berggren Forum will be given by Mark Lewis, Dean of College of Business, and Andrew Kless, Professor of History, and some of the students who traveled with them on an Allenterm trip to Germany when they visited Stuttgart, Heidenheim, and Munich just a month ago. The title of their presentation is Alfred Students in Germany Travel in COVID Times. This week, we're delighted to have Dr. Jessica Domino, who's presenting research that came out of her dissertation, which she defended successfully last spring in April. The title of the talk is Shake and Bake, How Natural Hazards Help Us Understand Earth. Dr. Domino, take it away.
All right, thanks a lot, Mallory. I think you did a good job by Emrys. All right, thanks everybody for coming to spend your lunch hour with me. I'm going to talk a little bit about what research I've done in the past couple of years and what my baby was for my dissertation. So before we get too into the details, I want to challenge everybody thinking about scale and perspective. On a daily basis, we think about where our offices are in relation to our classrooms and where our homes are in relation to our offices, and we think on a relatively small scale. If we zoom out from there, we can get a grasp of where we are in New York State, our relative location in Alfred to Rochester, Albany, New York City, but we're going to keep going out from there, possibly think about the United States and North America, where we know in New York, there was a tiny little town in upstate New York in relative to the entire United States that were thousands of miles from the West Coast and even further from Hawaii and Alaska. So zooming out even further, putting our size of ourselves and our town into perspective of the world, we then look at a global map. So this is just our general Mercator map, but the important thing to focus on here is the topography and bathymetry colors that we're looking at. So here, North America, we can see mostly green. These regions of brown are higher elevations. But if we look into the oceans, we see these these lighter colors towards the center, and they follow this linear feature through the Pacific into the Indian Ocean, and we see the same thing that's pretty symmetric on the Atlantic Ocean. And from there, we can kind of get a sense of how our Earth is constructed and made our continents in the situation that they're in today. So from there, we go into where do we shake? And we're thinking about the earthquakes that occur on and near Earth's surface. So we're looking here at the distribution of global earthquakes for the past year. These are all earthquakes for the past year. And we're looking at size distribution. The smaller the circle, the lower the magnitude. And those little blue colors, the brighter the color, the bigger the circle, higher magnitude earthquakes. And we can see the distribution of these earthquakes is around our continents and in these ocean regions where we saw that lighter color blue, where we have regions of high. And this gives us some question about the arrangement of our continents and why why our earthquakes are so focused in certain locations. So if we then start to think about where do we bake, right? We're talking about shaking and baking of Earth here. We bake pretty much around the same locations as a lot of those earthquakes. And here we're focusing really in on the Ring of Fire. and we can see most of our volcanoes and earthquakes, these really big natural hazards, are centered around that ring of fire. If we pull out even further and think about why this is, geologists in the last 60 some odd years have come up with this idea of tectonics. And tectonics is the way that I think about the world. And it's broken up into these different plates, some that are colliding into each other, some that are pulling apart, and some that are sliding past each other. And all of those motions provide this release of energy in the form of earthquakes, and in some cases we get volcanoes. So today we'll think a little bit about the ring of fire, and we'll talk about how earthquakes and volcanoes provide some information about Earth's structure. So just to give some reference, here's Mount St. Helens and that famous eruption in 1980. That's one that we're all pretty familiar with and learned a lot about how to deal with natural hazards on the West Coast. It was something that came up really quickly and affected a lot of people in a way that we hadn't been affected in a general population before. If we go across the Pacific now, still in the Ring of Fire, but thousands of miles away, looking at Mount Sakurajima of Japan, which erupted in January of 2013 in this wild eruption, that gave us more questions about how volcanoes and lightning are related in ways that we didn't understand before. Now we get a sense of understanding that the ash that's thrown up into the atmosphere during an eruption actually causes some charged particles to react with the atmosphere, and we get some lightning. So every time we get an eruption, there's some greater understanding, but also more questions. Then if we go down south a little bit to the most recent eruption, right, Tonga, which everybody has heard about, just a few weeks ago, it changed the way we think about volcanoes, especially on our planet, but thinking about them on other planets as well. This eruption was one of, if not the biggest recorded eruption in history. It broke all records that we had known of to be associated with volcanoes up until that point. And one of the things that was kind of unbelievable about it was that in our age of advanced technology and constant instant communication, this eruption cut that entire island and the islands around it off. And we could only get a sense of what was happening over there through satellite images, which is this one published by National Geographic. But this gave us some clues to similar processes that might have occurred on Mars. So we're coming up with new questions, and people are crunching numbers and publishing data that we figured out from an eruption just a couple of weeks ago. And then to round out the four corners of the Pacific, we'll look at Ojos del Salado in Chile. This was an eruption in 1993, and it's important because it is the tallest active volcano in the world. It sits at an elevation of over 14,000 feet, but it's still active. We get that magma reaching through that crust to feed those eruptions. So if we look at all four of these examples of volcanic eruptions in our historical recent past, what do they have in common, right? We're all around the Pacific Ocean here, yet we have some of the same natural disasters. And the answer is my favorite discipline of geology of all of them, and it's subduction. So subduction is where two tectonic plates are colliding against each other. We have oceanic crust that forms at these mid-ocean ridges. It's hydrated, it's relatively thin, but it's pretty dense material. Once it starts to collide with continental crust, it starts to descend beneath that continent. And since it's created with some of that, some water incorporated from it from our oceans, as it's descending beneath our continents, it changes temperature and pressure conditions. It's no longer happy with the conditions it's in, so it starts to dewater or release some of that water into this mantle wedge here, where we see those little water droplets that acts as a flux in the mantle, which is just beneath our crust. It lowers the melting temperature, and we're able to produce these melts that reach the surface and feed our volcanoes. So this is a process that we've studied extensively in the past 50 to 60 years, but is a relatively new and young idea in the concept of geology, only being accepted in 1969. So there's a lot to learn about our plates. And one of the regions that I focused on is where a place where this mechanism breaks down. So I looked very specifically along the South American subduction margin. It's the longest subduction zone in the world, and it's efficiently subducting oceanic crust beneath the continental crust. And it has been for tens of millions of years. So all along the western coast of South America, that oceanic crust is descending beneath the continent, and we see volcanoes on the surface here. There are two regions where we see these gaps in volcanism. And that's one of my focus areas, this southern section in central Chile, where there's been no active volcanism for the past 3 to 5 million years, even though we're still subducting crust. So something is happening with that flux mechanism, and my entire research career has been focused on understanding what's happening. So if we get a little bit of a closer look right here in between those volcanoes, we see a unique seismic pattern, but it's still seismically active. And we know that that oceanic crust is beneath the continent. And part of the reason we see decreased or no volcanism in this region is because there's some over-thickened oceanic crust that's going beneath this continent, and it's causing it to start to flatten out. So if we look right along here, we see some volcanoes out in the Pacific Ocean. They're part of this island seamount chain. It's not active anymore, but there are these old volcanoes on that oceanic crust that make the crust a little bit thicker, and it resists subducting a little bit more. We can follow the progression of that island arc subduction beneath the continent of South America. So here is a little video showing the progression and the evolution of what's going on. So we're thinking not only in a much greater spatial awareness and spatial scale, but we're also thinking in a much longer time scale today. So starting at 22 million years ago, we can see this chain was subducting much further north and has progressively moved southward and affecting the entire subduction zone as it is progressing southward. And there's evidence in the volcanic rocks up until its current location that volcanism was not active while that ridge was beneath the continent in those locations. So the big idea here, what I focused on, is understanding the missing magmas. What is the fate of the fluids that we know are going down beneath the continent, but aren't creating a flux to create volcanism on the surface? What is happening to them? So here we see this absence of volcanism. We know that north and south of this region, we have flux in the mantle. We have volcanoes on the surface that are totally active. These volcanoes just haven't been active for about 5 million years. And the proposed mechanism here is that we are flattening out, and then eventually it descends at a somewhat normal angle further back. If the fluids were released way back here, when it starts to descend at a normal angle again, we would expect really large voluminous volcanism in the back arc, something that we don't recognize. So trying to understand what's happening here. And to do this, I wear 2 different hats. We've gone through the introduction of what tectonics is, figured out the missing magmas problem, understanding the fluids. We're going to look at geophysics, how geophysics approaches this problem, the shaking aspect of our tectonic world, and then we'll look at the geochemical side, the rock side, the volcano side, the baking side of the geology perspective, and then we'll bring it all together. So here, the first part we'll look at harnessing the shake. So what can global seismicity reveal about material properties of that region where we don't have active volcanism in the flat slab region? And I used open data from IRIS and the Chilean National Seismic Network for this part of the project. So the big tool that I use or that I employ to figure out material properties is what we call these receiver functions. And it sounds scary, but all we're using is the P and the S wave from an earthquake. So every time there's an earthquake around the globe, it generates a P wave, which is a compressional wave, and then an S wave, which is a shear wave. The P wave is first, it'll arrive at stations first every single time. S wave is a little bit slower because it shears, it moves back and forth, and comes in second. These waves that come from really far away tend to, the distance between the P and the S wave increases. And every time a P wave hits a region of a big enough density contrast beneath the surface of the earth, it creates another S wave. So here we can see we're traveling through this red material, the P wave is happy, we get to this blue material and it's a different density or a different composition and an S wave is generated. When the P wave eventually gets to the surface and is recorded at a seismometer, we can read that converted S wave and then use that to understand the structure of the earth directly beneath that station. So we're looking at earthquakes coming in from all over the place. This is a station in central Chile that I use and generating a receiver function from earthquakes that are coming in from all directions. So to do this, I looked at thousands of seismograms, something that looked kind of like what we see on the left over here, just recordings of earthquakes coming into stations on the surface and constantly recording any slight motions. So I looked through it, really deep quality check and making sure we had good seismograms and good signal that could produce what we see on the right, which is the receiver function. So to do this, now going through all of the trouble to explain this really niche tool used in seismology, what's really the big deal here, right? There's pattern recognition between these red and blue squiggles. A lot of geologists don't like looking at the little squiggles, but these are really useful tools in identifying changes in both vertical and lateral seismic velocity perturbations. So essentially, we can find plate contacts where that subducting plate is located beneath a station, regions of melt generation, seismic anisotropy, which we'll talk about, associated with fluid-induced mineralization. So sometimes we can get fluid mineralization rather than fluid-induced melting, so that'll become important. And this goes, just to give some reference here, if we look at that same subduction zone next to a receiver function, I've put on a station here. That inverted yellow triangle is a seismic station on the surface. And we put them all over the place, located at very specific regions above plate contacts, and all of the earthquakes are coming in from really far away through this cone and collected at the surface. So all of the waves coming through will produce S waves generated at different density contrasts. So here we're getting a very small glimpse. This location right here, all the earthquakes coming in give us a general location of that plate contact. So here we can visualize the 3D structure beneath the station itself. But what I'm most concerned about here, we know where the station, we know where the crust lies. What I'm concerned about is what the material properties of that slab is and why we're not getting those fluids creating a flux to produce volcanoes. So here on this second part, this bottom section, the transverse section, that tells us how the waves are behaving as they're passing through that material, not just that it's a different material, but it tells us a little bit about that material itself. So to do that, what I'm looking for in this bottom section is what we call anisotropy. And anisotropy shows us lateral velocity changes. When we have an isotropic medium, waves travel at the exact same speed. They're together, they're totally happy, but as soon as we hit an anisotropic medium, it becomes directionally dependent and we get waves moving at different speeds. There's one direction that's faster than the other one slows down. So if we think about this as a wave coming up to the surface to a seismometer, we have an isotropic material. Those waves are together. As soon as they hit an anisotropic material, usually some kind of mineralization, it will slow one wave down and they'll get to that seismometer at different times, which we can record using the seismometer. Okay, so from here we can see directions north and south if they're coming in faster, or east and west if they're coming in a little bit slower, and it shows up as this four-lobed polarity flip on the receiver function. To put this in simpler terms, think about a field or a stadium that's pretty much a perfect circle for simplicity's sake. And we're all collected around the edges of this stadium. To get to the others, the idea is to get to the other side as fast as possible. And we can see in the middle here, there are some physical hurdles. And for all of us to start running at the same time, it's much easier and much quicker for the people going up and down or north and south to get through those hurdles than it is for people traveling side to side or east to west. So here we have a really fast direction, and then we have a really slow direction that's caused by this physical barrier between one side and the other. And that's very similar to what the waves are experiencing as they travel through an anisotropic medium. So I looked at over 150 stations in Chile within and around the Flat Slab region, detecting anisotropy, or looking for stations where anisotropy is detected. And I used the stations that were good and provided a lot of information about the material properties, and took this approach that is really important in the oil and gas industry, which we call seismic attributes. And seismic attributes essentially take qualitative analyses and translate them into quantitative data sets. So we only have a slight glimpse of one particular characteristic that we're looking at, and we can interpolate it across based on sample sizes. So I took all of that information from my stations, made a qualitative assessment of those receiver functions, and translated it into a quantitative data set to try to see the distribution of anisotropy in that location, so we could get a sense of the material properties in central Chile. So this seismic attribute interpolation, I did some inverse distance weighting interpolation and determined that regions where we have darker green indicate strong anisotropy, regions of these lighter greens, there it is, show minimal or no evidence of anisotropy. And this brings us to this conclusion that back here, where that slab starts to descend again, we don't have a buildup of fluid-induced mineralization. In this region within the flat slab, we have fluid-induced mineralization. So to bring it back to what this all looks like, north of the flat slab, where the flat slab has been in the past but isn't currently, it might have experienced some of that same fluid-induced mineralization that the receiver functions showed us exists in the flat slab today. And we don't expect the south of the flat slab to have experienced any of this fluid-induced mineralization because it hasn't experienced that flat slab subduction. So we get all of that from our seismology and from understanding earthquakes and how waves travel through different materials, but how do we approach understanding what has experienced that mineralization and what hasn't? And this is where we go into assessing the big time. So looking at the volcanoes, what can those volcanic rocks tell us about the conditions in which they actually formed? So specifically, figuring out where the magmas generated beneath the surface. So to do this, this is the exciting part. This is the reason people get into geology. We go out and we collect rocks. So I took a trip down from New York down to Santiago, Chile. And while we were there, definitely did a lot of rock collecting, but also did some of the unique cultural things and spent a lot of time in the fish markets, in botanical gardens, and in artist markets. But the most exciting part was actually seeing the volcanoes. So from Santiago, right here, this green triangle, we traveled up to the Atacama Desert. The region here between Santiago and Copiapó is the flat slab. That's the extent of the flat slab. Between these two cities, there is no active volcanism. Just north of Copiapó here is where the high Andes are and where we have active volcanism, and south of Santiago, we have active volcanism. So here are just some of the views from that fieldwork. This is Tres Cruces volcanoes, which are some of the first active north of this unique geometry flat slab situation. Here's our trusty little vehicle that got us a crossroads that did exist and a crossroads that we made up, and some of the beautiful volcanic views. And while it seemed very desolate, we were very seldom actually alone. Here are some flamingos drinking from the salars at the foothills of the volcanoes, way up in the Andes. These the elevations we were at here were over 6,000 feet, or 6,000 meters, about 12,000 feet. The tops of the volcanoes are well over 14,000 feet in elevation. Next, we went south. Traveled back down to Santiago and went south to Temuco, to volcanoes that were active down there to get samples of volcanoes or flows there. So here we can see that the regions and the landscapes look totally different. Here it's much darker. We see some snow. There's a lot more water because we aren't in the desert. And just trying to understand the differences in the chemistry north and south. So I collected all of these rocks, right? And what do we do with them, right? So I have these carts of rocks. I had to cut them down, try to get a pristine sample that was not weathered, not changed in any way from being on the surface. Ground it down using a couple of different mills to this size, slightly smaller than pebbles, but enough, just tiny little pieces. From there, they went into this shatter box. There's this container with a puck inside that we put on this latch, and we just shake it around until it becomes a powder, and essentially just homogenizing these samples so we can get a bulk elemental chemistry of what these rocks are actually made of. Once we had that powder, I put them in these little crucibles, these graphite crucibles, added a flux to them so they melt at slightly lower temperatures because these magmas are really high temperature rocks, threw them into a furnace, let them melt down, quenched them in some acid, dissolved it over time, and then used instruments such as ICP-OES, ICP-MS, and DCP-AES to understand the chemical makeup of these materials. So in lieu of showing really specific geochemical trends, I'm just going to focus on one. In geology, we tend to classify igneous rocks based on their amount of silica and weight percent silica. So this particular analysis was looking at rocks north and south of the flat slab that we collected that had a 55% weight percent silica. Comparing the same amount of silica helps us understand changes in other elemental compositions because we expect them to be relatively the same. This plot tells us a little bit about how or where that magma generated. So this depth to the Benioff zone is a fancy way of saying where the melt generated beneath the continental crust. And we can see here, if we're comparing all of these volcanoes from the Pacific Ring or the Ring of Fire, we can see that the rocks south of the flat slab generally fall in line with the trend that we see with the rest of the volcanoes, but the samples north of the flat slab are a little bit higher. This potassium that we read from these samples tends to be a little bit anomalous or especially different from south of the flat slab. So from here, we could get a sense that yes, they formed technically at the same depth. We see them plotting in the same region on the x-axis, but their y-axis is totally different, giving us an indication that yeah, they formed in the same places, but there's additional ingredients in this baking of the samples north of the flat slab, which we think has a lot to do with that fluid-induced mineralization from previous flat slab episodes. So wrapping all of this back up, why do we care about those really specific volcanoes and understanding the geometry of subduction zones? While they're super destructive, earthquakes provide a glimpse into Earth structure, and similar to CAT scans that we have for us, we get a sense of Earth's entire structure and material properties and how they might change over time. Volcanic eruptions give us clues for Earth's evolution and how magmas might change based on materials that are subducted beneath the crust. So understanding these Earth processes allows us to work with the threat of disaster rather than against it and prepare for future events. And that is what I have for today. Thank you very much. And if anybody has any questions, I'd be happy to take them.
Thank you, Jess. Please take a moment to type your questions into the chat, or I believe our tech support friend Mari will unmute you so that you can ask the question directly to Jess if you'd like. I'll start us off while people are collecting their thoughts, Jess, if that's okay.
Sure.
One question I have, you gave me so much information that I didn't know that I didn't know, and I'm grateful for that. I'm wondering, from your perspective, you talked about kind of finishing your dissertation last year, that this was your baby. I wonder what unanswered questions or curiosities do you have, or like if you had, you know, another 10 years to work on this, would you go in? Like what's next for this type of project in your mind?
So for this project, I used a lot of open source data and a lot of collecting of my own materials, but I used a lot of different volcanoes. And going forward, I'm hoping to focus on just a few volcanoes and getting stronger signals from more specific places than general trends. That's the idea going forward with this research.
Great. Thank you. There's some questions coming in the chat. David DeGraff is asking, can you comment on the role of water in volcanism and how that might affect the volcanism on Venus?
So water in volcanism is really important. It can determine the explosivity of that volcano. So usually with higher water contents, they tend to be more explosive. I've been reading a little bit about what's happening with the Tonga eruption and how seamount eruptions are affected by the oceans. And I've been reading about it on Mars and how it might give us some clues about how those eruptions happened in the past. I'm not sure about how it might affect volcanism on Venus, but water is really important. The more water there is, the more volcanically explosive that eruption tends to be, and is really important in subduction zones for even getting volcanism started.
Thank you. Laura Johnson has a question, and it says, how common are these flat slabs in subduction zones around the world?
Oh, that's a good question. They're relatively uncommon. We saw That very first, one of the first images I showed, let me bring it back up. This absence of volcanism in central Chile, but also in Peru. Those are two of the three that are known to be today. There's one a little bit further north in Mexico, but it's also been presumed that the Rockies of the West were created from a flat slab during about 40 million years ago. So they're relatively uncommon. The cause for them right now has been over-thickened oceanic crust, but there are other options for it, and we're kind of still in debates about that geometry, how it comes to be and how long it lasts. But it's relatively uncommon.
Thank you. Susan Steer wants to know, what do you think is the mechanism causing subduction?
The mechanism actually causing subduction is convection in the mantle, which drives plate tectonics altogether. So our plates are broken up into these, or our crust is broken up into these plates, that we can get a sense of the relative motion based on GPS measurements and satellite data. And some of them are breaking apart. So down here in the Pacific, along here, those two plates are coming apart based on convection in the mantle. It's pulling those two plates apart. And as they're coming apart, creating new crust, we also have to destroy some of the crust because Earth's radius is only going to stay relatively the same. We can't create new material without destroying some of it. So along these subduction margins, just purely, and it's a little bit more complicated than just density, but because that oceanic crust is slightly more dense and it's being pushed up against the continents, it subducts beneath back into the mantle and continues driving these density convection currents.
Thank you. There are no other questions in the chat right now. Are folks interested in unmuting themselves and posing any questions? I'm seeing gratitude in the chat for you, Jess.
Awesome.
Well, thank you, Jess, for all of this and for fielding our questions and growing our brains. And thank you, audience, for coming to our Berggren Forum and dealing with me. It's been a pleasure to try to be Emrys for the day, and I look forward to seeing you again. Oh, another one's coming in the chat, Jess, are you, if you can. It says from Becky, Craig would like to know more information on how your research will help in predictions.
Oh, that's tough. Geologists tend to stay very far away from using the word prediction because we know we will not likely be able to predict volcanic eruptions or earthquakes. We can forecast where they will be likely to occur based on past events and current configurations of plates, but the actual prediction of them is likely not going to happen anytime soon. But my research specifically, where we don't have volcanoes, understanding why the volcanoes aren't active in that region is important because we do expect in the future, probably millions of years from now, not in the near future, that it will be active again. So understanding how these geometries play into active and inactive volcanism gives us clues for how it can change in the future. Not quickly on our timescales, but geologically pretty quickly.
Thank you. Thank you. Thank you. Any other last questions? All right, join me in thanking Jess Domino for all of the wisdom that she has shared today. Thank you. I see lots of gratitude in the chat and applause on the screen. Join us next week for next week's Berggren Forum from Mark Lewis and Andrew Kless. And again, thank you so much. Bye, everybody.